Questions? No? Okay. Then let's start. So till now we have been doing brute force math, right? So today we will try to develop some intuition which will help us going forward without doing the entire HT tau thing for these kind of circuits. Okay. So hopefully this will break the monotony a bit. So what did we do? We basically said that this is the circuit we were interested in. Then we found out HT of tau, and the constraint we imposed after we found HT of tau was RC was much greater than TS, right? So with this we found, we found the transfer function. In fact, even without this, we found the transfer function. Imposing this, we imposed some constraint as to what the transfer function looks like if I plot it with respect to the input omega, right? So again, I'll just write it down. So if this is e power j omega t, so our h of j omega at t on, right? So again, at t on means this is t on. At t on and t on plus nts, right? So at t on was 1 by 1 plus j omega rc, which is the case you get in an LTI low pass filter times some extra stuff. This is 1 minus 1 minus, and here get e power minus t on over rc. And this is easier to remember because e to the power minus t on over rc is the amount of discharge that happens over one on time period. Here also you have e to the power minus t on over rc, and you have extra stuff. This is in the denominator. You have minus j omega t on. Here you have minus j omega ts. So we'll try to make sense of, intuitively we'll try to make sense of some of these terms so that our approximations make intuitive sense. So what we saw was, this is again a recap. What we saw was this guy, if we impose this constraint, RC is much greater than TS, and also maybe RC is much greater than T on. Let's say this is a stricter constraint. Let's say I impose this constraint. So if I impose this constraint, then what we saw was if I plot mod of h j omega comma t on with respect to omega, we saw some finite value at 0. We saw some finite at omega s, and then some at 2 omega s, and then 3 omega s. But again, we got a 0 at 4 omega s, right? Here we got something, but you got a 0 here, correct? And we also saw that between 0 and omega s, or between omega s and 2 omega s, basically around the vicinity of omega s, the value of this mod of h also drops. Correct. So sorry, I mean, I forgot to mention that we for this to happen, we needed to have the Ts by T on equal to 4, right? So that's true, because we had to, I mean, the intuition was we were averaging over one complete cycle, right? And thank you for pointing it out. In my mind, I am always thinking 4 paths. So I mean, so that's why. Okay, so and also we saw that this guy gets, this entire thing gets, can be approximated as 1 by 1 plus j delta omega in RC. In RC, where R equal to 4 in this case. This is h of j omega s plus delta omega t on. becomes approximately equal to this around omega s, which means that if obviously if RC is much greater than TS, NRC is naturally much greater than TS, which essentially means that if you deviate from omega s, you are getting a attenuation, correct? So basically we kind of without going through the entire plotting, we could kind of have an idea that this will look like this. Here also it will look like this, and so on. Correct? And maybe, I don't know, something is going to happen. This will going to connect somehow. And maybe, and here it's absolute zero. Right? So that much we understood. And then maybe if you go to 5 omega s, things are going to, these stuffs and values are going to repeat. So what I plan to do is give you an intuition without doing all this bunch of math, right? So as to how to go about thinking about it. This math was necessary because we wanted from the intuition will come from the math, and after that we are going to reuse the intuition. Okay. So let's see. So I have in that class where I gave a presentation of the works, I mentioned that if RC time constant is very high, then we can think of the voltage across the capacitor being an average over the on time of the switch. Yeah, right. It's basically the average value of the input over the on time of the switch. And average is nothing but the integral function. It's basically integral divided by some time. That's the time average, weighted average, right? So let's see why that statement makes sense. Okay, so now we are in a position to understand why that statement makes sense. Okay, so for that, before we go there, let me. Okay, so the intuition that I would like to provide is this. So before going to the intuition, let me ask you this. The intuition is as follows. Assume that T on is much less than RC, right? So then this guy is close to 1, correct? And assume that omega RC is much greater than 1, which means this goes to 1 over omega, correct? So if you think of it this way, these two terms, this term and this term, end up being 1 minus e power minus j omega T on by omega RC. Forget about the RC for the time being, but you kind of get this. Correct? Then you have some extra stuff. Here, extra stuff there. But you kind of get this expression.
Integral of x eta. Eta is some running variable, right? Let me use some different running variable, x, let's say x tau d tau. Note that this tau is not the same as the tau we have been using earlier, some running variable tau. And the integral will go from t minus delta t to t. What does this mean? This essentially means that the inverse Fourier transform of this is nothing but, if this is xt, is nothing but you fix some time t, right? And let's say this is t, and you go delta t away from here. All you are doing is doing the integral of this guy and taking the average of it, right? Now put it in context of what we are doing in our architecture. In our architecture, all we are doing is we are trying to evaluate the envelope. We are trying to evaluate the envelope when S of t is on, right? S of t is between 0 to T on, correct? So essentially in our case, what we are doing is the inverse, basically the inverse Fourier transform of this guy is equivalent to saying I am doing the integral of whatever this input, let's say Vi of t, I am doing the integral from 0 to T on, right? Because this is all we are interested in. And why not for all the other values? Why not for all the other values of beyond 0, right? This delta t I could have swept beyond 0 also, right? So delta t is this side, right? The delta t I could have swept beyond 0 also. The reason I am not doing it is because it is sufficient to evaluate the envelope for one cycle, right? In this case, we are interested between 0 to t on, right? But if I go beyond, if I go to the previous cycle, right, where I was between, say this is TS, I would have the envelope here in this duration will be identical to the envelope between 0 to t on, because it is a periodic sequence. I mean, it is an LPTV. It is an LPTV network, right? So in essence, wherever you find anything which is of this format, right, you know that there is some sort of averaging going on for a certain periodic, for a certain interval of time, right? In our case, that interval of time is t on, right? And by virtue of the LPTV system being periodic, right, I need not extend this delta t till infinity. I can limit it to the region of interest. In this case, in this particular case, our region of interest was between 0 to 2 t on, right? And that's what we are going to do. In order to get an intuition, or in order to in order to evaluate this in time domain, in order to evaluate the envelope in time domain without going through all this ht of tau business, what I would do is I will take the input sinusoid, right, and I will integrate it till the in the interval of interest, right? That's what we are going to do next.
Right? So then what is essentially, I mean, can you connect whatever we just discussed with this expression? Intuitively, what does this mean? I am integrating over a time of t on, correct? And denominator term is something extra that is coming. I don't know what it is. We'll talk about it later. But at least we see that. This gives you this gives you a framework to understand why I keep talking about I am integrating over a time period of t on. So this is not particular to this particular transfer function. Wherever you see this 1 minus j omega times t on or some t divided by omega, it is an integral. It is an integration that is happening in the time domain over a time period of t on. Right? The approximation that I made was this e power minus t on over RC is approximately equal to 1. If I don't make the approximation, then it's not an integration. It's some other thing. Right? So because I made this approximation of e power minus t on over RC is approximately equal to 1, that is RC is much greater than t on. Hence, this looks like I am doing an integration over finite time interval of t on. Had this approximation not been true, then clearly it wouldn't have been an integral. Like for example, if t on, if RC would have been much lesser than t on, that the top term would have been basically 1, right? The negative of e power minus t on over RC, that would have vanished in a broader sense, right? So under the condition that this RC time constant is much greater than t on, this combination of this numerator and 1 over j omega is telling us that some sort of finite time integration is happening. Okay, we agree? Okay, so if we agree with that, then it should make sense But now I will withhold my intuition about the denominator term for the time being. It will also come, right? But let's see what happens if we integrate the if we just follow our time domain intuition with respect to the integration. Okay. So now the reason I am going into this is because I want to see the transfer function evolve in time domain. Till now, what we have done the brute force. We have found out impulse response, and then we have Fourier transform to find out the harmonic response, h of j omega. Now I want to apply sin omega t, cosine omega t, and see what happens. And from there, I would like to come to e power j omega t. And that would be a much more intuitive way of going about seeing how the circuit works, right? Instead of doing math. So that's the motivation. Okay, so let's see. So if we agree with the fact that I have a finite window over which I am integrating, then what is happening? This set of switch is not required because it is not affecting. So what we will do, we'll apply sin omega t in one cycle, in one experiment, and we'll apply cosine omega t in another experiment, and then we are going to find out what's happening. Okay. So if I apply sin omega t, and for the to ensure that we do it for because so we understand this is a time varying system, right? So which means that it is also a function of the phase of the input, because if I change the input phase, it might land up into another domain of the with respect to the switches, right? So what we'll do is we'll apply a particular sinusoid at 0 phase to start off, and at a particular frequency also. We'd like to keep it to a frequency, known frequency for the time being, and then see how it evolves. Okay, so what we'll do is to start off, we'll keep it simple and say that omega equal to omega s. Okay, omega s, exactly the sampling frequency, switching frequency of the switch. Okay. So now, under the assumption that we are integrating, this is your input, and this is your T on, and n equal to 4, which means I am integrating over Ts over 4. Correct? So what do we get? So we get I'll integrate and do the average, right? So here, so because here I did not show, but when we expanded this, if you recall, we got that T on over RC term out, and ultimately there was an averaging over T on. The T on terms comes out, right? Do you recall? So, okay, so the other way of thinking about it is that at omega equal to omega s, this guy goes to 1, right? So you get 1 minus e power minus T on over RC. So 1 minus e power minus T on over RC is T on over RC. So in the denominator, you get T on, which means essentially you're averaging over T on, right? So that's what we are going to do. So we are going to average over T on. So, and if the input is a sinusoid and the output I am observing, so I'll typically call it omega WQ. That is the quadrature output. That's just the nomenclature. So you get 1 over T on, 0 to T on, sine omega st dt. So you get 1 over T on minus cosine omega st, 0 to T on. So this is, sorry, omega s will come out. Thank you. So T on omega s is 4 by Ts times omega s, and this is 1 minus cosine omega naught ts by 4. So this guy becomes pi by 2, so this guy goes to 0. So I get 2 by pi. Okay. Similarly, if I apply a cosinusoid, and I observe the voltage, what should I get? Without even doing the math, you should be able to tell me. It's the same thing, right? Because cosinusoid, I'll be. So this is T on. So I'm integrating over the same area, just the time shifted 1/4. So omega Wi also becomes 2 by pi, right? So this, if you apply now e power j omega st to your LPTV system, what should be your output? 2 by pi 1 plus j, right? Everybody okay with this? Okay. So this is exactly what we got by doing the brute force analysis. We'll get that also. But the magnitude of it makes sense, right? So the magnitude of the transfer function, so this is essentially mod of h of j omega t on is 2 root 2 by pi, right? Okay, fine. So this, I hope you agree that this is a much simpler way of finding out your finding out the transfer function. Okay. Similarly, now I will not do it here, but you can do the same exercise by assuming omega is not equal to omega s. Right? If omega is not equal to omega s, do it yourself. You are going to get some different number, some different expression, right? And that from that expression, you should be able to find out at what delta omega from omega s you have 3 dB drop from this particular value, right? And that should match with 1 over NRC, right? So you can do the math yourself, much simpler math than whatever we have done. It should match, okay? Okay. So now the question is this, if I apply e power okay, so before moving to the problem thing that I was trying to point out, can you comment on the fact that if RC time constant is very high, what should the output waveform look like for any particular, let's say input is any omega, input is a cosinusoid or a sinusoid of any particular frequency. The frequency is not changing. Input frequency is same. It might be omega s, might be multiples of omega s, might be anything. But what should the output look like? It should look like flat, right? We all agree with that, right? So it should be flat, which means it's almost a DC, right? Which means no high frequency component exists. Correct? Agree with that? So which means that if I put a band pass filter at the output at omega s or 2 omega s or 3 omega s, I should get near 0. Right? I should only get outputs at 0, around 0. Right? Then where does, then can you connect these two arguments, the argument that we had just now, with respect to this plot? Do you see a discrepancy between the argument that I made and this plot? What is the discrepancy? Here it is clearly showing that you have non-zero values. There are peaks at omega s, 2 omega s, 3 omega s. But from the arguments that we have been giving, it seems like we should have zeros. We should not have any. It should definitely not peaks. We should have severe attenuation at omega s, 2 omega s, 3 omega s. Yes.
But the value is flat till t on, and then after t on, it's a different value.
It is a different value, but if you recall the math that we did in the earlier classes, that deviation from that flatness is also almost negligible, right? If RC time constant is very high, right? If T on is much lesser than RC, then we showed that the term that dominates is essentially that H of T on only,
Yes.
right? So which means that regardless of whether you are looking at it at off time or on time, the value that you see across the capacitor is almost equal to the sampled value of T on. Make sense?
Yeah.
Right? I should not say sample value, whatever is the value accrued by the capacitor on T on. Right? As it turns out, the value accrued by the capacitor on the T on is the integration, the average over the cycle. That's what we showed here. And it keeps on holding on to that value for extended period of time. If omega equal to omega s, or even if omega equal to 2 omega s, the same arguments will hold true. Right? So then clearly this plot is, I mean, not clearly, I mean, if I step back with the argument that I was trying to make, this plot seems to be in conflict with whatever is happening. Yes. Yeah, fine. Aliasing back to DC, right? But then I should not be getting things at omega s, 2 omega s, 3 omega s. I agree that signal values can alias back. I do not have any objection with that. In fact, it is aliasing back. That's why, I mean, aliasing is nothing but another way of saying frequency shift, right? Frequency shift to a different bin is basically aliasing, isn't it? So that's what in fact is happening. And when you have mixing operation, you have aliasing. And because of that aliasing action only, even if you are applying input at omega s, it is appearing at 0. You apply input at 2 omega s, it is appearing at 0. That's why you're observing DC, right? But this plot seems to suggest that this is basically the brute force plot of mod of Hj omega T on. It seems to suggest that I am going to have peaks at omega s, 2 omega, 3 omega. So clearly something is not getting captured in this plot. Agree with that? Okay. So now let's see what is not getting captured and why is it not getting captured. So note that what we have done till now, in order to find this, what we did, we tried to find out the impulse response at one particular time, right? It is almost saying that now H of j omega T on is nothing but I sampled the envelope at that particular time T on. Okay. So now now I'll take you back to some basics. Signal processing. Are you aware of this concept of zero order hold? No? Okay. So let's say I have a signal. I sampled it at impulse sampled it at some rate. Basically, I multiplied it with an impulse train. Okay. So if I multiply with an impulse train, what do I get? I get this. I get strain of impulses weighted by the value of the signal at wherever it was sampled at, right? And then what if I tell you that what I am doing is in time domain, what I am doing is I am looking at this signal and holding that value for that period till the next sampling happens. Right? So essentially in the time domain, it should look like this. Right? So what is a mathematical model of zero order hold? That's what I'm after. Because the reason I'm after this is because if you think about it, in our case, what did we do? We basically said that we are finding out H of j omega t on, which means that I have values at t on plus ts, and so on. I have sampled these values. Whatever these values are, I have sampled that values, right? And then we are saying that because RC time constant is much, much higher than t on, these values are not going to change, correct? Over that cycle, over that entire cycle. These values are not going to change. It's going to hold on to that value. It's an approximation, but that's what we are saying. So which essentially means that it is similar to the zero order hold case, where I have sampled this value and I'm holding on till that, till one cycle. So it is equivalent to saying the impulse response for one sample is this, right? If I have a zero order hold, so if the input is delta t, the output is this. Correct? This is the impulse response of a zero order hold, because whenever I see an impulse, I replace the impulse with this truncated square wave, or you can ut minus ts. Correct? Okay, fine. Another piece of detail that is necessary is to understand that what is the, if I integrate the impulse, what do I get? Value is 1, right? So in order to ensure that the power content of the input and the output remains same, so we have to ensure that the integral of this is also 1. So this also gets scaled by 1 over ts. Okay, so this is an important scaling factor that you should keep in mind. So if we understand this, then it should make sense that your whatever h of j omega t on that we found, we should multiply with it with the zero order hold transfer function. So which means I need to find out the transfer function of this guy and simply multiply it with h of j omega t on. Right? So then what should I get? Then I will get the actual output frequency response across the capacitor when I have applied an input of e power j omega t. Right now we are getting the sampled responses at t on. We are not getting the continuous responses at t on. Right? So this plot that we had got, this plot is a plot of the sampled response at t on, not across all t. But we are making the leap that the voltage value at t on will remain same. Right? So which means that I can impose this condition of zero order hold with respect to the sampled value at t on. Correct? So all we have to do then is to multiply the transfer function of zero order hold with whatever we get here and then see. Okay, fine. So let's do that. So this transfer function is easy to get. So what will this be? Yeah, so it will be 1 by j omega ts, then 1 minus. Okay. So this is h of zero order hold. Fine. So I can express this as minus j omega ts by 2 times e to the power minus j omega, e to the power j omega ts by 2. So this becomes twice of j sine. And this 2 and this guy becomes, I can take this 2 out. So I can rewrite this as, yeah, sync, right? So sine of pi t. Okay, hold on. Yeah, pi f ts, right? by pi f ts. Correct? So what does, if I plot this with respect to f, what should I get? What should it look like? It should have a, at 0, I should get 1. And we should have zeros at, yeah, so basically f equal to, yeah, fs, 2fs, 3fs, and so on, right? Or in terms of omega, if I plot, I should get zeros at omega s, 2 omega s, 3 omega s, and so on. So I should get something like, if I plot the mod of 0 order hold, I should get something like this. Correct? And what was our h of j omega t on? So this was something like, and so on. So when you multiply these two, so naturally, this kind of goes to 0. I mean, it will not be monotonically 0. It will be something, probably something like this. I don't know. I mean, you get the point. And so on. Right? So essentially, we come to the consistency that you're at omega s, 2 omega s, 3 omega s, you are going to get zeros. Make sense? Does that make sense?
1 0.
Yes.
Hold. But e to the power minus j,
Hmm.
s by 2 into sin function of pi of ts.
Mhm.
So here, sir, when the omega value increases,
Mhm.
that exponential term will dominate more than as compared to that of the sin.
You mean the e power minus j omega ts by 2? But that is always 1, right? Mod is 1 for that. Right? I'm not taking phases at all till now, right? So phase is basically the point that you pointed out, there was a J issue there, right? So the issue will go off if you use this extra stuff, right? So that J will be taken care of. But if we just consider on the value, mod value, then this is what it is. Right?
So the initial expression that we found out
Hmm.
for h of j omega,
Hmm.
it's not giving us the complete information, right?
It is only giving you the information of the sample value at T on.
Sample value at T on.
Yes.
So it's not giving us the Fourier transform of the voltage across the capacitor.
Not for continuous time. It is giving you, let's say you have the continuous time voltage. You sample it at intervals of Ts shifted by T on. Then you are going to get a response, right? That h of j omega t on is that is the Fourier transform of that.
That is the response at the instances. Then we need to multiply the 0 order rule.
Correct.
So that's the
So other way of thinking about it is this, right? So since he's pointed this out, so let me also give another intuition as to who had those kind of plots, right? So if you understand, so from where did that plot come from? That came from this, right? So we had this h of t of tau, which was something like this. Correct? So we did the Fourier transform of this, and for this it came to be whatever it was, okay? So approximately, I can think of this as, even though this is, what I'm going to tell is an approximation, not strictly true, but you should be able to hopefully appreciate the fact that this probably looks like, if RC time constant is much higher than T on and all, it probably looks like I had a continuous decay of like this, and I have chopped it off somewhere here, right? So clearly, I mean, here, this and this are not equal, but which is a matter of detail I'm ignoring. So it is equivalent to saying that I have taken this function and multiplied it with a square wave, correct? Of value, I mean, this is T on, and this is TS, right? Make sense? Sorry, I mean, I did a mistake here. So it is equivalent to saying I confused you more than clearing. So you have this, and you have multiplied this with this guy. So if you do that, then you kind of get this, right? So this is this classic 1 by 1 plus j omega RC, right? And when you multiply with this, you are convolving in frequency domain. This, so basically, what I'm trying to say is this will have a transfer function of 1 by j omega RC, the classic RC time constant transfer function. And this will have a Fourier series. I mean, it's the Fourier's, the frequency domain interpretation is you have tones here, you have tones here, tones here, tones here, everywhere. So this guy gets convolved, comes here, one copy comes here, one copy comes here, and so on. Right? And hence you get those things, right? So there is a multiplication of with respect to a periodic signal happening, kind of. That's why you are getting this kind of broken discharge, right? And if because of that, you are seeing this repetition of the impulse of this 1 over j omega RC shifted across, right? So now, so the point, the reason I emphasize on this is not only it gives you kind of an intuition as to why this is happening. It also emphasizes the fact that we are only interested if you take any continuous time waveform, right, and you sample it, and you only look at the samples, you are going to get in the frequency domain replicas of the Fourier transform of the continuous time signal. Now, if the continuous time Fourier transform is band limited, right, then the replicas won't overlap with each other, and you are going to get chunks of those replicas everywhere. If they are very wideband, then they are all going to overlap. Then we call aliasing, and they are going to intermingle and do something, right? But in this case, if RC time constant is much higher than T on, then it's band limited for all practical purposes. Hence, it is getting replicated across multiples of omega s. Okay, does that make sense? Okay, so hopefully, I mean, I am trying to connect from different domains, and hopefully this clears things up more than confusing you. I mean, basically pick whichever way of thought gets to you, right? So there are multiple ways of looking at the same thing, right? So you want to look at it from time domain, you look at it from time domain. You want to frequency domain, fine. Brute force maths, fine. But as long as we are clear of whatever is happening, we are okay. Okay. Any questions? Okay. So the next part will be easy, is because now we have only looked at, I have more or less covered the difficult parts. So we have been looking across the capacitor voltage, and that's what we saw. The capacitor voltage will be like this. I mean, you might recall that in that 1 hour presentation that I gave that day, and this was probably covered in 5 minutes. Okay, in intuition that why it is like this, but now we know the math behind it. Okay. Okay, so now I'll take the next step. This part is similar to what we did in that day's lecture, that once we have the voltage across this capacitor, I want to find out the voltage at this node on the other side, right? So this should be very simple. What should I do? Multiply with S of t, right? Which means convolving with the impulses of the transform of S of t, right? So S of t has, this is exactly what we did like 2 minutes back. This is S of j omega. So you are going to have 0 omega s, 2 omega s, 3 omega s, 4 omegas will be 0. And this guy will get convolved. And you're going to get this. Okay? Make sense? Okay? So now, if I only look at, let's say, this replica, if I only look at whatever is happening at omega s, why am I interested there? The particular reason I'm interested is because e power j omega t, if, let's say, omega is approximately equal to omega s, right? And I'm applying an input, this is an LPTV system. I'm applying an input at e power j omega s t or omega t around omega s. And I'm observing the output at omega s, right? So given the fact that I know that your V naught is e power j omega s t times the transfer function, where the transfer function is hk j omega s e power j k omega s t for all k, right? So which hk am I looking at? What value of k am I looking at? If I'm input is at omega s, output is at omega s. Look at it carefully. If k equal to 1, what do I get? If k equal to 1, what is V naught?
0.
E power j omega s t times h0 j omega s e power j omega s t, right? So this and this gets multiplied and the output should be 2 omega s, right? I'm observing at omega s, which means which value of k should I look at? 0, right? So if input is at omega s and the output also is omega s, then the what? Correct. Yes. Correct. Thank you. So this is for k equal to 1. So we are looking at k equal to 0, right? So which means that if we apply, okay, so which means that the value that I'm getting here is essentially h of 0 j omega s. Okay? Make sense? If I have to look at, if I'm applying e power j omega s t, and this is my LPTV at RC at omega s, you can basically the R switched RC that I'm looking at, and I am observing at 0, right? So then which h of k am I looking at? Right? So this is k equal to -1, right? So basically h of -1. So where should I look at? So maybe I'll redraw this because I don't want to go up and down multiple times. So this we verified that this is h of 0 j omega s. If I observe at DC, the volt, this is the envelope at on the left-hand side of the switch. Be mindful of that fact, right? So it is important to keep track of at what point am I looking at, right? This is the envelope on the left-hand side of the switch. If I look at the envelope on the left-hand side of the switch and I observe the value at omega s, the peak that I am getting is the 0th sideband. right? Which is a fundamental sideband, essentially, right? If I have to find out the -1th sideband, right, what should I look at? No, -1 means left side, right? So this I should get H -1, right? And so on, right? So at one shot, right? So all we did was find out the transfer function at T on. That's all we did. And that is not very difficult to do, right? You can do it by the way I showed it today in time domain. You can do it by brute force method, either way. You can find out the transfer function of j omega not T. You can find out the voltage across the capacitor and then multiply it with S of t, and then you get this waveform. Moment you get this waveform, you look at the peaks, and from the peak you can make out what is the what are the side bands of hk that comprises of that LPTV transfer function. Make sense? So just to tie things together, there is a way of expressing. So the point that I was, the expression that I had written. So h j omega t, right? This is for any LPTV, not necessarily RC. For the RC transfer function that we RC switched RC network that I am talking about, for any LPTV, this becomes h of k j omega over j omega t j omega skt. Did I miss the k there? No, I had it fine. For all k. So this I can, in a block diagrammatic sense, I can sketch it as your. So if I apply an input of e power j omega t, so I will multiply everything with e to the power j omega t, right? So in a block diagrammatic sense, I can say that if you have an input that is e power j omega t, it is getting multiplied by a series, a parallel combination of blocks. One is with H0, H -1, H1, and so on. H0 goes straight through. No, H0, what is the subscript for H0? K equal to 0, right? So H0 goes as is. H1 gets multiplied by for j omega st. H -1 gets multiplied by e power minus j omega st, and so on. Each of them, the nth one gets multiplied with e to the power n omega st, right? So, and you then sum them up and you get V0, right? So all we were doing so far was trying to find out H0, H -1, H1. We did an example to find out what this will be. This is the result of before switch. Correct. Very good. So if I want to do the same thing after switch, that is across the capacitor, what will I get? So what will be H0? Now this you should be able to tell that intuitively. Approximate is fine. I don't want exact answer. So the voltage across here will also I can express as HKC, let's say I call it C now, or voltage across, or HCK. That probably is a better way. HCK e power j k omega st for all k, right? So what will be HC0? Oh, by the way, before I finish, before I move on rather, the H0, H -1, are they independent of omega or dependent on omega? Or rather independent of input or dependent on input frequency? Dependent, right? Because this is this. That is for value when the input is at omega s. If the input is at a different frequency, that value changes. Correct? So this is also a function of omega, input frequency. The very important thing to remember. These are not constant. I mean, the way to think about this is, let's assume this is an LTI network. If this is an LTI network, how does this picture get modified? No multiplier, only one straight line, the H0. And in that case, do you think the H0 will be a function of omega? No. See, if input is equal to j omega t, you have RC circuit. It will be a function of omega, right? So if that is a function of omega in LPTV, basically should be, must be, right? By the way, there is a name for this this type of reduction. It's called ZADEH, right? It's called ZA polynomial way of expressing this LPTV block diagram, right? Okay, so nomenclature apart, how much time we have? About 5. So okay. So can you tell me, when I am taking the voltage across a capacitor, in principle, this is still an LPTV network, because capacitor is a part of the network which is switching. Now, if that is true, so I should be able to find out all these H0, H minus 1, H1, everything, right? So what will be H0? How to go about thinking about it? And use all the approximations, think of all the approximations that we have done till now. So in order to find out H0, again, I should not say H0 only, I should also say H0 at what frequency, because it is also dependent on frequency, right? So let's say I am interested in H0 j omega s. What will HC0? You know everything, now give me a value. This will be a value, right? We agree, right? H0 at a particular frequency, this should be a value. What will this value be? Why? So one thing, when you are finding out H0, you have to first establish what is the input and what is the output. What is the input? No, input means what in this case? So what input frequency is whatever is in the parenthesis. Correct? So this is the input frequency. So e power j omega st. What is the output frequency? It's the sideband number times omega s times the input frequency. Correct? So your output frequency is equal to input frequency plus sideband number times omega s. Correct? So when I am finding out H0 at output, which frequency am I looking at? At omega s I am looking at. So in this network, what is the strength of the output at omega s? Think about it. It will be 0, right? It's a low pass, right? At the end of the capacitor is a low pass. We did all these things, 0 order hold, everything, and blah, blah, blah. Why? Because it was going to 0, right? So your H0 is essentially 0, right? What is HC minus 1 j omega s? What is the input frequency? Omega s. What is the output frequency? To evaluate this, I need to find out, look at the output at, basically you can assume that I put a band pass filter at the output at certain frequency. At what will be the center frequency of the band pass in this case? 0, right? So what will be that value that I'm going to see at the output of that band pass filter? 2 root 2 by pi, right? So this will be 2 root 2 by pi. Mod of this will be 2 root 2 by pi. Okay. What will be, if I say that, what will be HC0, 0? What is the input frequency at? 0, right? Input frequency is 0. What is the output frequency? 0. What will be the value? Why 0? So input is DC. Will the output be 0? If the input is a DC voltage, will the voltage across capacitor be 0? input is a DC of 1 volt. What will be the voltage across the capacitor? 1 volt, right? So what will this HC0 of 0 be? 1. Right? It should come out from this only. I mean, it's not a rocket science, right? So if you, in this expression, if you put omega equal to 0, so you get this, these two will tend to 1, right? Limiting value tend to 1, you are going to get 1. Isn't it? Okay, one last thing let's do. One last, what about HC -1 or +1, let's say. +1 at 0. Output is at, input is at 0, output is at omega s. So what should I get? Means 0, right? Okay. So the note that we have done this with number of ways. One is that finding out HT of tau, putting that value. But today what we did, we took the assumption there's a high RC time constant and related this with averaging, and we only found out the transfer function from an averaging activity of the input sinusoid. So I did it only for the particular case of omega equal to omega s. Satisfy yourself by doing it when omega is away from omega s, maybe omega equal to multiples of omega s. These are all various combinations of things that you can try out and match it with the transfer function brute force that we got with brute force. Okay, you are going to see that there can be slight amount of differences, right? But we can talk about the differences later on, right? That if you do not take phase into account, there can be slight amount of differences. Okay. The other thing that you need to know is, understand is, the voltage across the capacitor only exists around DC, but the voltage at this node, will have multiple sidebands, among which the sideband, 0th sideband, that the one at omega s, is basically the upconverted version of the capacitor voltage at omega s, right? So in other words, if you apply input at omega s and you only observe the output at omega s, and you, let's say I make another modification of this and say that here I'm going to put a band pass filter at omega s, right? So and this is, let's say, my final output. Okay. So then for the user, what would the user find? The input is at omega s, output will only be at omega s. For the user, for all practical purposes, this is an LTI system, because this bandpass filter has knocked off everything else. Input is at omega s, output is at omega s. If I move omega input at certain frequency, if I move input from omega s to omega naught, I am saying that I have also moved this bandpass filter omega s from omega s to omega naught. So I can fool the user in thinking that this is an LTI system, right? And so the user would find that this is a LTI system centered around omega s. Correct? In this particular case, it would seem like it's a LTI system centered around omega s. And let's say I do not move the center frequency of the bandpass filter. We keep it at omega s. Then what will the user see? User see that I apply an input at omega s. I am getting a finite value at omega s. If I move away from omega s, suddenly drops, right? And which means it's a very sharp bandpass filter, right? And what is the sharpness? The sharpness is essentially what is the bandwidth? of this, or rather, I should say this one. What is the bandwidth of 3 dB bandwidth of this bulge? 1 over NRC, right? So I can basically say that omega 3 dB is 1 upon NRC, right? And your omega naught is basically omega S. So your Q is omega S by 1 by NRC times NRC, basically. Correct? So I ignored a factor of 2 because when you, 1 by NRC is basically one-sided for the low-pass filter. In this case, it's two-sided because I have to take this side also, that side also. But the key thing to note is that the Q factor is dependent on N, dependent on R, and dependent on C. All of these are user controllable. It's no longer dependent on the value of L and C, or L can be very bulky in the, you cannot, L will be lossy and all those things, right? Even if I fix R and C, I can keep on increasing N to get more and more sharpness. And what's more, I can move the omega S also. What is omega S? It's basically a clocking frequency. It's a band pass filter with a electronically programmable center frequency with seemingly arbitrarily sharp Q factor. Right? Make sense? So that is the power of just one switch. Okay, and that is why these kind of circuits are becoming very popular in the recent years. Okay, yes.
That in the end, HC minus 1 came out to be root 2.
So what is the input here? J omega S. What is the output? Okay, so output across the capacitor when the input is at omega S. Right? The average value or the voltage across the capacitor when the input is sine omega st or cosine omega st, J of that, right? Okay, we'll stop here.